Here is the reaction coordinate of ethylene oxide and diethyl ether when they undergo a nucleophilic substitution reaction with OH- as a nucleophile. As you can see from the reaction coordinate, it is very clear that ethylene oxide is more reactive than diethyl ether. And that is because of the ring strain in the three-membered ring structure of epoxide. And that is the reason why we needed to not apply heat when we conduct a nucleophilic substitution reaction on epoxide. Epoxides can undergo nucleophilic substitution reactions under all conditions, acidic condition, basic condition, and as well as neutral conditions because they are very reactive. If you take a symmetrical epoxide, it is going to give us only one product, but the mechanism is going to be different. Here is an example for a symmetrical epoxide. The first step, the oxygen with its lone pair of electrons is going to go abstract this hydrogen, and it's going to give us a protonated epoxide. And protonated epoxies are in general very reactive, and therefore they can be opened up even by very poor nucleophiles such as water or alcohols. So let us say that you have an alcohol here, which is going to make a nucleophilic attack on one of these carbons. Here there is no preference because both of these carbons are equally substituted. And therefore this nucleophile will go and approach this carbon in a side that's opposite to that of the three-membered ring structure. Okay. And it will break open this bond, or it will open this ring structure, giving rise to a product. So here in this case you have a proton still intact here, but in the presence of a base, this proton will be abstracted and the positive charge will be neutralized to give the final product. The base catalase mechanism also going to give exactly the same product, provided the epoxide that you're going to start with is symmetrical. Okay? But you need to make sure that the nucleophile that you take should be a stronger nucleophile. So let's say that we have methoxide ion or ethoxide ion. So this methoxide ion will go and attack one of these carbons, and then it will break open this ring. Okay? Here it doesn't have any preference because both are equally substituted. And again, it will come in a direction that's opposite to that of this ring structure. Okay? And it will break open this ring. So once you have your negative charge on that oxygen, this is going to go grab a proton from either acid or even methanol. Okay, and form the final product. So as long as you start with a symmetrical epoxide, it's going to result in exactly the same product under both acidic and as well as basic medium. When you take an unsymmetrical epoxide, a nucleophilic substitution product that will be obtained under acidic conditions and neutral and basic conditions would be different. Let's see how this is going to be different. So under acidic conditions, it's going to pretty much follow the SN1 mechanism. Okay, where the nucleophile will go and attack the most substituted carbon, whereas under neutral and basic conditions, it's going to follow the SN2 mechanism, where the nucleophile will go and attack the less sterically hindered carbon. So let's look into the mechanism again. So oxygen with its lone pair of electrons, it's going to go grab this hydrogen, okay, and it's going to get protonated. So once you have the protonated epoxide, the next step is your nucleophile. The nucleophile is going to go make an attack on this. Okay, let's say we have methanol as a nucleophile. This nucleophile will now go and attack the most substituted carbon. So between these two carbons, this is the carbon which is highly substituted, and therefore it will go and attack this carbon. So it's going to pretty much follow the SN1 mechanism, and it's going to break open this ring. And in the next step, methanol will go and abstract this hydrogen and neutralize this positive charge to give us the final compound. So this is the compound that we'll be getting. But let's see what is going to happen when we conduct the reaction under neutral or basic conditions. So under neutral or basic conditions, we have a strong nucleophile and it's going to follow the SN2 mechanism. So between these two carbons, which one is less substituted? So this is the carbon that is less substituted, and therefore this nucleophile is going to go attack this carbon and it will break open this ring. And this O minus will grab a proton to get it converted into OH. And now you can see that the two products are different, right? So look into this. The OCH3 has got it added to the carbon, which is highly substituted here, but here it got added to the less substituted carbon. Okay, so these two products are definitely different. So when you have an unsymmetrical epoxide, this is the carbon that will be attacked under basic conditions, whereas this is the carbon that will be attacked under acidic conditions. So basic conditions or neutral conditions for here. Okay.